Welcome to an in-depth lesson on stacks and subroutines in assembly programming. A stack is a last-in, first-out data structure, like a stack of plates where you can only add or remove from the top. Let's understand the fundamental operations and behavior of stacks. The two basic stack operations are push, which adds an item to the top, and POP, which removes the top item. On the 68,000 processor, stacks grow downward, from high memory addresses toward low memory addresses. When you push data onto the stack pointer actually decreases, moving toward lower memory addresses. The 68,000 has a special register dedicated to stack operations. Register A7 serves as the hardware's stack pointer, making it special among address registers. The 68,000 actually has two stack pointers through A7, USP for user mode, and SSP for supervisor mode. Let's see how to create and initialize a stack in 68,000 assembly. First, we reserve memory using ds.l for 256 long words. Then we initialize A6 to point just past the end of the allocated space. The stack pointer A6 is initialized to point to the top, which is the highest address, just past the allocated space. The 68,000 uses addressing modes for push and pop operations. To push, we use pre-decrement mode. This decrements A6 first, then stores D0 at that location. To pop, we use post-increment mode. This loads from A6 into D0, then increments A6. When we pop an item, the stack pointer moves up to the next item, and the topmost value is retrieved. The PEA instruction is specifically designed for pushing addresses onto the stack. PEA pushes the effective address of label onto the runtime stack. This is equivalent to moving the address of label onto the stack with pre-decrement. Byte operations on the hardware stack have a special behavior. When performing byte operations on A7, the stack pointer is adjusted by 2 bytes instead of 1 to maintain word alignment. Even though we're moving a single byte, the stack pointer decreases by 2 bytes from C000 to BFFE. You can access stack data without modifying the stack pointer. This copies the byte at the top of stack to D0 without changing A7. Using displacement addressing, we can access data at any position relative to the stack pointer. The most recent item is at SP, and earlier items are at positive offsets like SP plus 2. MOVEM efficiently saves or restores multiple registers at once. To save registers, we use MOVEM with pre-decrement mode. To restore registers, we use MOVEM with post-increment mode. When saving with pre-decrement, registers are stored in order from D0 through D7, then A0 through A7. Multiple registers are saved efficiently in a single operation, preserving their values on the stack. Subroutines use the stack to manage return addresses. JSR pushes the return address onto the stack and jumps to the subroutine. RTS pops the return address from the stack and returns to that location. JSR calls the subroutine, and RTS returns execution back to the calling code. Parameters can be passed to subroutines through the stack. Pass by value means we push the actual data value onto the stack. We push the value of variable A onto the stack. Pass by reference means we push the address where the data is stored. We use PEA to push the address of variable A onto the stack. Parameters are pushed first, then JSR pushes the return address. Inside the subroutine, we access parameters relative to SP. Inside the subroutine, we access parameters using displacement addressing. The first parameter is at 4 bytes offset from SP, accounting for the return address. The second parameter is at 8 bytes offset from SP. Transparent subroutines save and restore registers they use. At the start, we save registers we'll modify. Before returning, we restore those registers to their original values. After saving registers, parameters are now further from SP, so we must add the size of saved registers to offsets. After saving registers, the first parameter is now at 20 offset from SP4 for return address plus 16 for saved registers. After a subroutine returns, the caller must clean up parameters from the stack. LEA adjusts the stack pointer to remove parameters, here removing 4 bytes. Calculate cleanup amount by multiplying the number of parameters by their size in bytes. Let's summarize the key concepts of stacks and subroutines. Stacks follow last in first out order and grow from high to low memory on the 68,000. Register A7 serves as the hardware stack pointer with separate user and supervisor modes. Push operations use pre-decrement addressing, while pop operations use post-increment. The MOVEM instruction efficiently handles multiple registers in one operation. JSR pushes the return address before jumping, and RTS pops it to return. Parameters are passed on the stack and accessed using displacement addressing. For transparent subroutines, always save registers at entry and restore them before returning. When you save registers on the stack, remember to adjust parameter offsets accordingly.